Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, minimum number of visited cells in a grid. The problem states that you are given a zero index matrix M cross N and you are initially at the top left cell 0, 0. You will start like from the cell I comma j, you will be able to visit all the cells I comma k where k lies between j and grid ij plus j. Similarly, you can visit any cell k comma j where k again lies between I to grid ij plus I. For example, let's say you are currently at the cell 0 comma 0. So from 0 comma 0, you can visit the current value of the cell is 3, right? So you can visit any cell in the in 0 comma 1, 0 comma 2 or 0 comma 3. Similarly, you can visit any cell in 1 comma 0, 2 comma 0 or 3 comma 0, right? So you are able to perform these movements. Now you have started at top left cell and you have to return the minimum number of cells that you need to visit to reach the bottom right cell, that is m minus 1 comma n minus 1, right? So you are at 0 comma 0, you have to reach m minus 1 comma n minus 1 and you have to return the minimum number of cells that you will be visiting during this journey. Now this is very standard problem wherein you are given a graph in disguise of a matrix and you are asked to find out the shortest distance between two nodes 0 comma 0 and m minus 1 comma n minus 1, right? So you can just visualize this each of these nodes, each of these cells as a node and these transitions as the edges in the graph, and simply you can simply do bfs to figure out the shortest distance between the cell 0 comma 0 to m minus 1 comma n minus 1. Now why bfs and why not Dijkstra? Because the edge here, each of this edge are of equal weights. So if you go from 0 comma 0 to 0 comma 1 or 0 comma 2 or 0 comma 3, everything you have the weight of 1. Basically that contributes 1 to your answer because you are visiting one extra cell, and that's what the question cares about. Because each edge has equal weights, Dijkstra and BFS both will give us the same answer, and because BFS is simple both to implement and in terms of complexity, we will use BFS here, right? So if you are new to this concept of a graph representation in terms of metrics, I can link a small introduction video in the description below for you. You can check that out first before jumping ahead. So for now, I assume you know how to like represent this in a graph, and we can simply do BFS to figure out the answer. So the pseudocode for that would look something like this. We will push 0 comma 0 because that's what the initial node that we are at, and for we will just pop out the top node, and for each node we will visit all the cells in the rightward direction and all the cells in the downward direction, right? Now for each cell we will first check if it is visited or not. If it is not visited, then we will visit it, and because we are visiting this cell for the first time, we will update its distance as well, right? And similarly, we will push it to the queue as well because this is the first time we are visiting this cell. And after this, we'll also mark this cell as visited. That I haven't depicted here, but that there is one more step that would just mark these things as visited, right? Now, what is the time complexity of this entire algorithm? First of all, we are pushing to the cell only once, like pushing one cell to the queue only once, because we checked before that it is visited or not. So we are pushing to this queue only once. So that's where we will be popping from the queue only once. So this pop or this entire while loop will run into will run for r cross c time, basically one time for each cell. And for each cell, we are doing two loops, one this and another one this, right? Now what is the worst case complexity of these two loops? So basically this says that I will be visiting from r plus 1 to r plus grid rc. So in worst case, it can visit all the r rows in the uh, given matrix. Similarly, this can also visit all the C columns in the given matrix in the worst case, right? So R cross C time this is running, and for for each R cross C you can in worst case visit R rows and C columns. So in total, the complexity of this entire algorithm is R cross R plus C. This would not pass because the given problem r cross c is 10 to the power 5 and r and c themselves can be up to 10 to the power 5. So this would surely not pass and you have to optimize it. Now, which of the factors can you remove? First of all, you can't remove these factor at all because you need to visit each cell exactly once uh, to do anything in the matrix, right? You have to visit each cell once at least, right? So this is something that we are targeting to remove. Now, why this exactly comes in the first place? Because we are iterating over each of the possible edges from the current cell, right? Now, can we reduce this? The answer is yes, but how? So think about it. Why this is giving you R plus C complexity, and why not something less? So first of all, let's say from this node you are traversing to this three nodes, right? So after this, you have traversed these three nodes. So let's say you have marked this as visited. So this cross means they are visited, right? Now after you have marked them as visited, let's say you pop out this node from the queue, right? Now you again visit this node and this node, but you will not do anything for these two nodes. Why? Because these you will figure out that they are already visited and you will just continue from here, right? You will not execute the actual uh, lines of code that would give you the distances, right? So these lines of code are not getting executed for each node that you are visiting here, and that's where we have some sort of duplication, which is leading us to R plus C. Let's say somehow we are able to remove these two lines completely from our algorithm. So in that case, what we are saying is we every time we enter this loop, it is certain that we will always insert something into the queue, right? Or in other words, we will always visit a new node completely. Now, how many times this can be done? Again, you can only push R cross C time because there are only R cross C distinct nodes, right? So then the amortized complexity of this entire algorithm would be R cross C. Again, just to reiterate, what we are saying is we saw that we are revisiting some nodes in the follow-up while expanding a follow-up node, and because of that we are not doing, like, we are not actually doing the things that we would have done for a new node, and that's what leading to an extra complexity. So what we have this thought is, let's remove this line completely from the uh, algorithm, and we will somehow, like, we'll not iterate over everything for sure, we will somehow figure out which all nodes in this range are yet not visited, and we will visit only those nodes. And because we are doing that, we are saying that every time we enter into this loop, we'll be pushing something to the queue, and we already know for the fact that we will only push into the queue R cross C time because that's that many nodes we have at the end, right? So then the amortized complexity of this entire thing would be R cross C. So now the reduced problem is we have to remove these two lines from our algorithm somehow. Now, if you have watched the previous week's lead code contest video, there as well we have applied the exact same trick. So if you have watched this particular video of previous week, I would strongly encourage you to pause the video right away and try to think of the solution by yourself. If you haven't watched that particular video, then watch this video till the end and then try to solve the other problem by yourself, or or try to watch that other video as well. That will give you a different way of implementing the same kind of algorithm, and you will be getting much more insights on when to use this trick that we are discussing in this video, right? So with that, I hope you have thought about the solution. Now let's look at the actual solution. So the target is we have to remove this line from the code. So what this mean? It means that we need to somehow maintain a list which only gives us the non-visited uh, indexes, right? So let's say you are at 0 comma 0, right? For each row you maintain a list of indexes or list of columns that are not yet visited. So let's name this remaining columns, right? So you are maintaining a list of column for each row that are not visited, and the array name, the data structure name is remaining columns. Now, what you will do, let's say from 3 you visited this. So okay, so first of all, we have to visit everything in the range r plus 1, or we can visit everything in the range r plus 1 to r plus grid rc. So currently r is 0, so we can visit everything in the range 1 to 3, right? But we will only visit those which are not yet visited. So what we can simply do, we can simply go to the row 0, right, and figure out these all columns are something which are not visited, right? So because these all columns are not visited, we can simply figure out which of these columns fall under this range 1 to 3 and visit those completely, right? By visiting them, I mean we will remove this from our data structure completely, right? Now, after this, let's say you visit this node, right? So once you visit this node, you will again figure out that okay, I need to visit, or I can visit everything in the range. Like this node has 0 comma 1, right? So you can say that okay, I can visit everything in the range 2 comma 5, like c plus 1 to grid rc plus c, right? Now we will again go to row 0, right, and figure out which of these column in this range are not visited. You will get nothing, so you will not do anything. Previously we were visiting these two cells and then figuring out that they are visited by this line of code, but now we are not at all visiting these cells because of this new data structure that we have introduced. So we don't need this line as well, and because we are able to remove this line, our uh, problem, we have removed r plus c from time complexity completely, and we have introduced some complexity for this data structure. We will look at that complexity afterwards, but that's what the crux is, right? Now, what this data structure would be. So what we are doing exactly, we are doing two things, right? We are removing an element from this data structure, and we are also finding or doing upper bound and lower bound, right? Because we need to figure out that which of these ranges are lie between a current L comma R. So we have to do upper bound and lower bound. So we need a data structure that can actually remove an element, keeping the order sorted, and also give us upper bound and lower bound without like in log n time or something of that sort. So just pause the video and think about a data structure for this. The answer is set. So or any balanced binary search tree that can give, that will help you removing an element efficiently and also will give you upper bound and lower bound. So the data structure that we are maintaining is vector of int of set. So basically we have three sets. Each set denotes the columns which are not yet visited for a particular row, right? So for row 0, these all columns are not visited. That's what this set denotes, right? So now having this data structure with us, we can we can we saw that we will only visit each node exactly once, and hence the complexity is reduced from r cross c into r plus c to r cross c into some complexity of the data structure, which is log n here, because every set operation is log n. So this log n would be introduced. So, uh, but there's one more thing which is missing. The missing thing is we maintained a set of non-visited columns for a particular row, but we also need the same thing for a particular column. So let's say we are at column 0, right? And we know that we can visit this and this, right? Now it may happen that these two are already visited somehow, so we are wasting time, right? So that's where we have to remove this statement for column as well. So we will just maintain another data structure of same kind, which will give us the same information but column wise. So basically it says that for column 0, row number 012 are not visited. Similarly, for column 1, row number 012 are not visited, right? So now these are the two things that we need to remove this is visited line from our algorithm completely. So let's just iterate over a simple example and try to wrap this up. So we are initially at 0 comma 0, right? So we will look at how many rows we can visit, or how many columns we can visit from this row and how many rows we can visit from this cell. So we are at 0 comma 0, so we can visit any row like 0 comma k, where k lies in the range of 1 to 4, right? Sorry, 1 to 3. Similarly, we can visit anything of the form k comma 0 where k lies in the range 1 to 3, right? So let's take this thing first. So what we are saying is we are visiting row 0 and we want to know how many columns between 1 and 3 are not yet visited. So we'll simply do a upper bound here in this list, or lower bound, whatever you want, and figure out that these are the cells, or between these two pointers all the cells are something which are not yet visited, and they lie in this range as well. So what we'll do, we'll simply visit them. So let's say we visit this one first. So basically we visit 0 comma 1 first, right, and push it to the queue, and also remove it from our data structure. Now notice one thing, we have removed 0 comma 1, right? So what this also means is for column 1 row 0 is gone, right? So we have to also remove this one, right? Just to reiterate, we have removed 0 comma 1, which means that column 1 for row 0 is not valid, which in turn also means that row 0 in column 1 is not valid. So we'll also remove this, right? Now again, moving forward, we will remove this because this is the next element. So we will push it to the queue, right? 0 comma 2, and the same way we are saying that column 2 of row 0 is not valid. So row 0 of column 2 is also not valid. And finally, we will remove this as well and this as well and push 0 comma 3 to our queue, right? So this is what we have done in the rightward direction. Let's now go in the downward direction. So what we are saying is we want to know all the row in the range 1 to 3 in column 0 which are not yet visited. So we will visit column 0, figure out how many cells are there in the range 1 to 3. So there are these two pointers are the left and right pointers. So we will visit them and remove it from the data structure as well. So we will visit this, right? So basically we are visiting 1 comma 0, right? And we will remove this from the data structure. So we will, once we remove this, it means row 1 of column 0 is not valid. So we will remove this one as well because this also represent the same thing. Similarly, we will remove this and push 2 comma 0 to our queue, right? And this is now gone. Now in the same exact same fashion, you will do other things as well. So let's just take one last example and we'll conclude this. So let's say we pop out 0 comma 1. So now currently you are at 0 comma 1. So it means you can visit any cell of the form 0 comma k where k lies in the range 1 to 5, right? Because current value of column is 1. So you can visit anything in the range 2 to 5, right? So what you will say is, okay, give me for row 0, give me all the columns in 2 to 5 that are not visited. So for row 0, give me all the columns starting from 2 until 5 that are not visited. So you will get this pointer. So basically the lower bound upper bound will point to the end of the array. It means there is nothing at all which is lies in this range. And the same thing you will apply for downward direction as well. So basically you will say for you can visit anything in the range k comma 1 where k lies in the range 0 to 4, right? So again you will go here. So sorry, 1 to 4, right? So you will go to the column 1, right? Ask what all ranges are there which lies in the range 1 to 4. So again you will find these two, you will remove this one and push 1 comma 1 to the queue, and because you have removed this one, you will also remove this because this also represents the same node, right? So hope you got the intuition what we are doing. So the total complexity would be order r cross c into log r or log c, whatever is the maximum of that, because what we are doing, we are actually uh, inserting one node exactly once into the queue, and after popping it we are doing some like lower bound operation and also some removal operation. So both will take log n time, and hence the complexity would be r cross c into log n, where n is the max of r and c. So this is the pseudo code for the same thing. Previously, we have visited all the columns in this fashion, but now we will be visiting all the columns in slightly different fashion. Basically, we will ask for how many rows are not this remaining row, the remaining columns of our store, how many rows of column are not visited. So we'll just ask the lower bound of c plus 1. That's where we will start from, right? We'll start from c plus 1, and we'll go all the way up to c plus grid of rc, and we will keep on iterating until we reach c plus grid of rc, right? And notice that because this vector or this data structure only contains non-visited cells, we don't need this is visited line here at all, and we simply do these two operation, right? And finally, we have to remove this thing, this row, this current cell that we have just visited from both the data structure as well, right? So if you have followed through this, just pause the video right away and try to code this solution yourself and try to submit it yourself as well, because this is just addition of two new data structure and using the data structure to remove something to just maintain the fact that what all cells are remaining, right? So hope you have at least tried the solution yourself. Next, we'll look at the code. So the code is exactly similar. We have two data structures, remaining rows and remaining columns. Remaining rows denote for a particular column C how many rows are remaining. Similarly, remaining columns denote for a particular for a particular row R how many columns are remaining, right? So we initialize both of them with all the rows and all the columns, right? After that, we initialize the distance vector. Everything is initialized to -1. Basically, it doesn't the path to them doesn't exist, and we initialize 0 0 to 1 because we are initially at 0 0. Now we push 0 0 to the queue, and we will keep on popping from the queue until it is empty. Now after popping, what we are doing, we have to apply this thing. Basically, we will ask, we'll go in the rightward and the downward direction by asking remaining rows and remaining columns array. So first we will ask remaining columns that okay, for row R, how many columns are there which are greater than equals to c plus 1, and we will keep on iterating over the columns until we reach c plus grid of rc, right? Now for each of these r comma c, we will do these two operations, right, which was standard dfs that we have just looked at, and we are inserting this new column that we just used in our erase columns vector. Now notice that we could have removed, like we have to remove these two things, right? But we can't remove it directly inside this loop, because in c++ if you do this, uh, the iterator would then become invalid. So that's why I am pushing everything, like I'm not mutating the data structure while I am using it. I will do mutations afterwards. So that's the standard technique. We just accumulate all the things that we need to remove, and after this loop we iterate over all of them and we erase it from both the data structure. And the exact same thing we have to do for the downward direction as well. We will query for how many columns or how many rows are there for a particular column C, which lies in the which starts from r plus 1, and for all such we will keep on iterating it until we reach r plus grid of rc. And finally, we will again push it to the vector so that we will not mutate the data structure while we are using it, and we will finally erase it from our data structures, right? So this entire thing would run in order r cross c into log n, and this would fit in the time complexity that is given. So hope you enjoyed the problem. Again, if you are new to this concept, I would strongly encourage you to watch this part of this video, minimum reverse operations, which is from the previous week lead code contest. I would link it in the description down below, and somewhere in the top right eye section you can watch it. And this problem also it uses exact same trick. It also uses set to to segregate the indexes which are not yet visited from the visited ones. So hope you enjoy it. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.